Good evening, sir. My name is Jala Bashan. I am from ECEC 24BQ1A04I7. Today my topic name is about functions of momentum. Subtitle is characteristic functions of momentum generating functions. Function of a momentum that calculate the nth momentum of a random variable x. Two functions are generally used to characteristic functions and momentum generating functions. Characteristic functions definition for a random variable x with probability density function f(x) of x, the expected value of e power j omega x is called characteristic function. Phi of x is equal to phi of x of omega minus e of e power minus j omega x. Here w is the real variable minus integral to less than or omega is equal omega less than infinity. J is the imaginary unit. J square is equals -1. For continuous random variable, phi of omega is equals integral minus infinity to infinity e power j omega t fx of x dx. For a discrete random variable, phi of x omega is equals summation I e power j xi p of xi. Properties for a characteristic function transforms the random variable x into another real random variable omega. It can be expressed from the Fourier transformer for fx of x with the signature of omega received. Use phi of x omega fx of x are the four transformer pair. Inverse four transformer. The probability density function fx of x can be obtained back from the phi of x omega. Using inverse Fourier transformer, fx of x 1 by 2 pi integral minus infinity to infinity phi x of omega e power minus j omega x dx d omega. Summary: phi of x of omega is equal characteristic function of x. It is the Fourier transformer of fx of x. Fx of x can be obtained as the inverse Fourier transformer phi of x omega. Here, phi of x omega and fx of x are Fourier transformer pairs. Theorem: momentum of characteristic function for omega phi of x is equals to omega is the characteristic function of a random variable x, then the nth momentum of a x is given by the m by n of minus j power omega dn omega x of it omega dm d omega n. Step 1: characteristic function of a definition. For a random variable, x is the characteristic function of omega x of omega is equals e power j omega x. Step 2: series expansion from e power j omega x. The Taylor series expansion is e power j x power x is equals 1 plus j omega x plus j omega x whole square by 2 factorial plus j omega x cube by 3 factorial plus so on. Subtraction for expression. Taking expression omega x is equals omega of e power j omega x is equals 1 plus j omega e of x minus omega square by 2 e power of x minus j omega cube by 3 factorial 2 3 factorial e of x cube plus so on. Omega x of omega is equals m naught plus j omega mn minus m square by 2 m square m2 j omega cube by 3 factorial by m3 plus so on. Where when m4 is equals e power e of x power n is the nth momentum. First derivative define. We know height omega d square omega x by omega by d square omega x by omega by d omega is equal jm minus omega m square minus j omega square by 2 m cube plus so on. At omega is equal to 0, j omega x of omega by omega m is equal to 0 is equal to j m1. Hence, m1 is equal to minus j d omega x by omega by d omega. Omega is equal to 0. Step 5. Second derivative. D square omega x by omega x of omega d omega square is equals minus m square by j omega m cube plus so on. At omega is equal to 0, d square omega of omega by d square omega is equal to 0 minus m square by j square m square. M2 is equals minus j square by d square omega of omega by d omega square. Generalization. By continuing the definition process, the general form of d power n omega x of omega by omega n, where omega is equal to 0 is equal to j power n mn. Therefore, mn is equal to minus j of n dn omega x of omega by d omega n. Properties of a characteristic functions. The characteristic function is unit at omega is equal to 0 and the given by phi of x of omega is equal to 0, phi of x of 0 is equal to 1. Proof. The characteristic function is given by the phi of x of omega is equal to e of e power j omega x at omega is equal to 0, phi of x of 0 is equal to e power 0 is equal to e power e of 1 is equals 1. The maximum amplitude of a characteristic function of a unit at omega is equal to 0. Phi of mod phi of x phi x of omega less than or equal to phi x of 0. Proof that the characteristic function of a phi x of omega is equal to e of e power j omega x. The amplitude of a phi of x omega is equal to phi of x mod phi of x omega is equal to mod e of e j omega x mod integral minus infinity to infinity fx of x e of j omega x dx. Since mod xy less than mod x mod y mod phi x of omega is less than or equal to integral minus infinity to infinity mod e power j omega x mod fx of x dx. Mod fx of x omega less than or equal to integral minus infinity to infinity fx of x mod dx. Since mod e power j omega x is equals 1, therefore mod phi of omega less than or equal to 1. Proof. We know that phi of omega is equals to integral minus infinity to infinity e power j omega t fx of x dx. Since omega is the continuous e power j omega is also continuous. Here phi x of omega is continuous function. Fourth one. Examples. Phi x of minus omega and phi x of omega is conjugated functions. That is, phi x of minus omega is equals phi x of star omega, and phi x star is equal minus omega is equals phi x of omega. We know that phi x of omega is equals e of e power j omega x. Phi x of minus omega is equals e of e j of minus omega x. Phi x of minus omega is equals to e of e j omega x is equals to e of e power j omega x star. Phi of x minus omega is equals phi of x star phi. Movement generating function. The movement generating function mgf of a random variable is also used to generating the nth momentum about the region. Consider a random variable x on with a probability density function fx of x. The moment generating function of x is defined as the exported value of the function of v e power vx. It is can be exposed by mx of v is equals e of e power v of vx minus where v is a real variable minus integral less than v less than plus integral infinity minus infinity less than v less than infinity. Mx of v is equals minus integral minus infinity to infinity e power vx of fx of x dx for a discrete random variable x mx of v is equal summation e power vx I v of xi theory. If mx of v is a momentum generating function of a random variable x, the generating then the nth momentum of x is given by the mn dn d power n mx of v dvn. V is equals 0. Proof. Consider a random variable x with a momentum generating function mx of v is equals e of e power vx. We know that series expression for a e power vx is e power vx is equals 1 plus vx square by 2 factorial plus vx cube by 3 factorial plus so on vx n by n factorial plus mx of v is equals e of evx is equals e of 1 plus vx plus v square x square by 2 plus v cube x cube by 2 plus so on vn x n factorial x power n so on. Mx of v is equals e of 1 plus v x plus v square by 2 e of x